we're going to start to talk about derivatives that are higher than the ones we've been talking about before. What I mean by that is instead of taking simply one derivative, now we're going to start talking about taking two derivatives. So to do that, let's take a look at an example. Suppose a leak from a pipe has occurred. At a time t hours, g of t gallons of water has leaked, where g of t is given by the function g of t equals square root of t. What does the first derivative of g, evaluated at 1, or g prime of 1, tell us about the leak? So to start out, we need to go ahead and take the derivative of g, and I'm going to think of g as simply being t to the 1/2. That's what square root of t means. That allows me to use my power rule, so when I do that, I end up getting g prime of t is 1/2 t to the minus 1/2. Now that I have it in that form, I'm going to go ahead and take the reciprocal, because that's what that negative power tells me to do, and then convert it back to a square root. So that leaves me with 1 divided by 2 square root of t. Now it's a lot easier to plug in t equals 1. G prime of 1 is equal to 1 divided by 2 square root of 1, which is equal to 1/2. So right now, I know that g prime of 1 is equal to 1/2, but since this is in the context of an application, I want to look at this and see what the units are that are attached to it so I can help interpret what's going on. So in this particular problem, we know that g prime represents a slope, and our rises are in gallons, and our runs are in hours. So when we do a slope, we're going to end up with gallons per hour. At t equals 1 hour, the rate is 1/2 gallons per hour. That means that each additional hour at that point, 1/2 gallon of water leaks out of the pipe. Now let's ask the same question, but now let's ask it at t equals 4 hours. So I need to take the derivative that I found earlier, and I need to plug 4 into that. So g prime of 4 is equal to 1 divided by 2 square root of 4. Square root of 4 is 2, so when I work that out, I get 1/4 gallons per hour. That means that each hour an additional 1/4 gallon of water leaks out of the pipe. Now you notice that it went from 1/2 gallons per hour to 1/4 gallons per hour. Since the rate at which water is leaking is getting smaller, in some sense the leak is getting better. What it really means, though, is that the rate is decreasing. It was going from 1/2 gallons per hour to 1/4 gallons per hour. So what would another derivative tell us? In other words, if I take the first derivative, which I've already found right here, and I were to take a derivative of that, what would that tell us? So to do that, I need to take my 1/2 t to the minus 1/2 and take the derivative of that using the power rule. To help symbolize that I'm doing two derivatives, I'm going to write that out with 2 primes instead of 1 prime. G double prime, or the second derivative of g with respect to t, will be minus 1/4 t to the minus 3/2, and I'll go ahead and write that as negative 1 divided by 4 times the square root of t cubed. Remember that the 1/2 power that's in that minus 3/2 gives me the square root, and the 3 comes from the 3 that's on the top of that fraction. The fact that it's downstairs means that it had a negative power here. So now let's go ahead and put a value in there. If I put 1 into the second derivative, I get negative 1 divided by 4 times the square root of 1 cubed, which gives me negative 1/4. Since we're asking about how is the rate changing now, because this is another slope, it's going to end up being gallons per hour per hour. Remember, the derivative to begin with, the first derivative, had units of gallons per hour. When we do a slope on that, that essentially divides by hours again. So we get gallons per hour per hour. What that means is that each additional hour, the rate at which water leaks decreases by 1/4 gallons per hour. It decreases because this was a negative number right here. Another way to write out gallons per hour is just to say gallons per hour squared. And that comes from the fact that if we take gallons per hour and divide it by hours, that's the same as taking gallons per hour and multiplying it by the reciprocal of hours, or 1/hours. When we work that out, we get gallons per hour squared, because hours times hours gives us hours squared. But remember, you can always break it back into gallons per hour to help you interpret what's going on. So in a sense, this number is telling exactly what we saw earlier, that the fact that our leak went from a 1/2 gallon per hour to a 1/4 gallon per hour, that means our leak was getting, the rate was getting less. That's exactly what this number is telling us. But now it actually quantifies how much less for each hour. So the notation for higher derivatives is very similar to what we've already talked about. The second derivative of y equals f of x can be written in any of the following notations. It can be written with 2 primes, like we've just seen, so f double prime of x. It could be written with the dy dx notation, but now what you'll see is that there's a 2 between the d and the y, and another 2 on the bottom. That 2 is basically saying that you're taking 2 derivatives. And it can be written as d sub x 2, and that means that you're taking 2 derivatives with respect to x. We can do the same thing with the third derivative by doing a triple prime, or putting a 3 in the dy dx notation, or putting a 3 in place of the 2 in the dx notation. If you go any higher than 3, you're going to start to run out of room. So in that case, we go ahead and up in the power. Instead of writing 4 primes, we just write f with a 4 in parentheses. If y is equal to x cubed plus 6x squared minus 6x plus 10, let's go ahead and find the second derivative. So whenever we need to find a second derivative, we first have to find the first derivative and then take its derivative. So when we take the first derivative, dy dx, the derivative of x cubed is 3x squared. The derivative of 6x squared is 12x. The derivative of minus 6x is minus 6. And the derivative of the constant 10 is 0, so it doesn't appear here. So my derivative is 3x squared plus 12x minus 6. Now when we take another derivative, and I'll write that as d2y over dx squared. The derivative of 3x squared is 6x. The derivative of 12x is 12. So our second derivative with respect to x is just 6x plus 12. Basically, all we're doing is just doing 2 derivative problems in one. Let's go ahead and try a slightly more complicated derivative. Let's take f of x equals x times e to the x and find the second derivative. Now you'll notice here that this is a product, so I'm going to let u be the x and v be the e to the x. That means that u prime is going to be 1 and v prime is going to be e to the x, because the derivative of x is 1 and the derivative of e to the x is e to the x. Now I'll go ahead and use my product rule and write out what the derivative is. So when I do that, I get v, which is e to the x, u prime, which is 1, plus u, which is x, v prime, which is e to the x. When I look at that, I notice that both of these terms has e to the x in it. So doing a little algebra, I'm going to factor out that e to the x. What I'm left with then is e to the x times the quantity 1 plus x. The reason why I'm doing that is because I want to make it easier in the next step to take another derivative. I have another product here, so now I'm going to have u be e to the x and v be 1 plus x, and now I'm going to take another derivative to get my second derivative. So f double prime is going to be v, which was the 1 plus x, u prime, which was the derivative of e to the x, plus u, v prime. So e to the x times 1. So my product rule gives me the quantity 1 plus x times e to the x plus e to the x times 1. Just like in the previous step, I'll notice that there's an e to the x in both of these terms, and I'm going to factor it out in front. What that will leave me with is 1 plus x plus 1, which combines together to give me x plus 2. So the second derivative here is e to the x times the quantity x plus 2.